Okay.
It's 14.
Let's start off with a definition. And the first things that we're going to talk about are pretty straightforward, and it's going to be review for most of you, especially Calc 3. It'll just be represented a little bit differently. Let me make sure that's recording, actually. Okay, good. A matrix with only one column is called, and this is going to be a shocker, I know, a column vector. People ask why I'm so literal. It's because I study mathematics. Sometimes we just call this a vector because I don't want to say column vector every single time throughout the course. So here's some examples. It's very straightforward. What does it mean to have only one column? Well, it can have as many rows as we want, but this would be a column vector, right? It's how many columns? Does it matter how many entries? No. Okay. I could have more entries if I wanted. I could have something like this. Is this a column vector? Yeah. How many columns? Okay. Does it matter how many entries? No. Okay. So what I'm hearing is I can have an arbitrary number of components. Is that still a column vector?
Yes.
Why? It's only one column. Beautiful. Okay. Next definition. Vectors A and B. I'm going to be very, very picky throughout the entirety of the class about notation. If you are writing a vector, the Calc 3 kids already know this. You're putting a little arrow over that. And for the reason that we're going to have scalars and vectors. So notice that these don't have arrows over them, and that's because they're not vectors. These are representing scalar quantities, so real numbers, like 1 or 7. This is indicating to me that that's a whole vector. That's going to have its own component, so we need to distinguish what those are. So if you answer a question correctly, but you notate it wrong, I will count it 0. Sound good? Okay. These two vectors are, we consider them to be equal to each other, if and only if, meaning that these are logically equivalent statements. Their corresponding entries are equal. And the reason why we have this definition is just to safeguard against uniqueness of vectors. So for example, I would not say that the vector minus 7, 1, 1, this is not the same thing as 1, 1, minus 7. Okay? The order of these entries matters. This is describing a completely different vector than this one. In a similar sense, this is also not the same as 1 minus 7, 1. Okay, so we are not allowed to shuffle around the order of our entries. If you shuffle them around, you've created new vectors. Yeah?
Yes.
Okay. So, in order to say that these vectors are equal to each other, I'd have to say minus 7, 1, 1 is equal to what? Minus 7, 1, 1. Every single entry needs to correspond for two vectors to be equal. So far, so good?
Yeah.
Okay. Okay, let's do some algebra now. So we're going to put some properties on this, some operations. Given two vectors, let's call this u, v. There's the symbol in. You're going to see that probably 4,000 times this semester. A double strike r represents the set of real numbers. And if we superscript it with something, that's telling me how many times we've taken a Cartesian product of it with itself. You've probably seen that notation many times. As a refresher, R2 is the simple way to describe just a Cartesian plane, R3 for three-dimensional space, etc. Okay? So Rn is simply saying it can be general. We can have n number of entries. So how many entries are in this vector right here?
3.
So this would be a vector in R3. There you go. So if these are two vectors in Rn, then both vectors have how many entries?
N.
Okay. Their sum is a vector as well, is the vector that is known by, so if I take u and I add it to v, the same thing as saying, okay, so I have start with U1 components. How many did we say that there's going to be in Rn? So we have U sub n plus, and then V sub 1 up down to what? V sub n. And what we're going to do is we're just going to add the corresponding entries together. So I'm going to put all the V's together. So U1, I'm going to add that to V1. That's going to happen all the way down. When do I stop? What's the last one here? Yeah, UN plus VN. So if you took Calculus 3, you recognize the mechanic. We're just visually representing it in these columns instead of in the bracketed rows. Does that make sense?
Yes.
Okay. Do you need an example to see how addition works, or are we feeling pretty confident that we can do addition?
As long as they're equal.
I like the honesty. I'll do an example.
No, you just got no.
I'm taking it that was a joke.
Yeah.
So what I'm hearing is that you will be able to add vectors, and I won't be disappointed that you can't add vectors.
Interesting.
I'm doing an example.
Scott, 1 second.
Yes.
In the last definition where it shows R, is that an apostrophe N or apostrophe 2 for the R?
R2.
That's R2?
Oh, sorry. Yeah. So this, I was just doing this as a separate example. So like,
But in the definition itself, what is the apostrophe, what is in the...
oh, this is a comma.
No, apostrophe of the R.
At the end.
R to the n.
That's
Okay,
the
thank
end.
you.
Yeah. So n is like a positive integer, say
Yeah.
7. Everybody, what's the first one?
7.
Wow, and then
0.
you should have your degrees already. Why are you still here? Okay. Okay. Let U in Rn. So, in math language, a vector U has how many entries? That's how I want you to read that, okay? And then C in R. So if now you're given, notice, is there an arrow over that? No. Why? It's just a real number. We're going to call these scalars. A scalar. Then the scalar multiple. Again, this should be review, but just visually it looks a tiny bit different. Scalar multiple of my vector U by the scalar C, which is a real number, is the vector, again. I take my scalar C, I multiply against the vector U. Suddenly, notation really matters. What if I didn't put a line over U? Then you have a scalar product of just two scalars next to each other. So this is, it becomes important. So I have scalar. Now, how many components were in my U vector?
1.
N. Okay, so I start with U1 and I go down to what? And that is going to just scale every single one of these up. So CU1, CU2, all the way down to CUN, whatever that last one is. Okay. Again, I'll just do a quick example so that we see actual numbers instead of the general form. If I took 7 times a column vector 8, 0, negative 1, then what is that going to be? What's the top one? Middle one? And bottom one. There we go. So we can do the only two operations that let us put together linear combinations and therefore do some vector equations. Okay? Okay, so graphing vectors is going to be very, very similar to how we graph points. If you want a visual representation of what we're actually doing when we have these vectors floating around, so if I said some x is equal to AB, x is in R what? How many entries?
2.
So I'd say x is in R.
2.
There you go. So this would correspond visually if I had, say, plotted in R2, here's x1, here's x2, and it could be some vector, doesn't matter what, this is described by A, and this is described by B. Nothing new, nothing crazy. You've seen that a million times. And so same thing if I had some vector y equal to alpha, beta, gamma, I would claim that y is in R what? Y is in R3.
There's 3 entries.
3 entries. And so the only really difference that the Calc 3 students are going to have to get the habit out of is not calling this x, y, z. It's going to be the components of this vector. So it'll be the x1 component. Whoopsie, I actually made a mistake. Should be y. And why is it y? It's because I called the vector y. So that's my bad. This is y1, y2, y3. Okay? And then I should have studied art before becoming a math teacher, but that's not bad. Okay. So this component along the y1 is the alpha. So visually that would be alpha. And then along y2, the second component is beta. So the distance that this traveled along here is beta. And then how tall we are is the gamma value. Okay? We cannot really plot this in higher dimensions, so I'm using these two as examples. Yes?
Making sure if you have a question on any exam or anything that's basically you need to do a graphical representation of it, do you want us to basically still follow like XYZ orientation, or does that matter? Like if it was like a 3-dimensional, you don't care that Y1 is going to be on top or bottom or left, like do you care?
Very good question. You still want to follow the right-hand rule. Okay, so in the order, if you have R3 specifically, follow the right-hand rule for, this would be equivalent to the x-axis, this would be equivalent to the y, this would be equivalent to z. And then just label it according to the name of the vector and then subscript it accordingly. Does that make sense? Okay. So if you think about plotting Cartesian coordinates, you should be fine for the most part. We're not going to do a ton of graphing, but the graphical intuition will definitely be helpful in random moments of time throughout the class. Now I know that the addition is really, really obvious when we look at it from the mathematical perspective, but there is a really, really satisfying visual way to think about this too. We call this parallelogram rule. Fun fact of the day, I didn't know how to spell parallelogram until I was in 10th grade, and I would always put one L here and 2 L's there. For addition. Okay, so essentially, if I have it's x1, it's x2, if I take some vector in R2, say like u, and then another vector, v. And then if I want to think about what it's really to add them, if I added these two vectors, you've all seen this a million times in your physics notebooks, right? It'll be, there's a parallelogram, and then that furthest away point is where the location of the head for this sum is going to be. And so we all see the parallelogram rule. But there's a really, really fun way to kind of visually justify this, and I call that head to tail. Head to tail. Real quick, for the anatomy of a vector, we are going to call this end the tail end, and we're going to call the point where the arrow is, we're going to call this the head. So just to make that clear, so that we know what we mean by head to tail. Head to tail is going to say, okay, so I'm going to go from u, head, and if I imagine just taking my v vector and sliding it up to fill in this, you don't really need to think of the whole parallelogram. What you're really thinking is, I journeyed that far up, and then I just attached the tail of my other vector right here, and then it ended up moving out to where I wanted to be when I added it. Even further, if you think about just the components strictly, you have your first chunk of component here, that's going from here to here, and then the remainder of that component from here to here. So at the end of the day, you're just summing up along a number line in one direction for that direction, and then along this direction for the remainder. Do you need to think about that visualization whenever you add vectors? Please don't, okay? When you're doing just regular addition, you can just perform the addition. But it's good to know what the parallelogram rule is if you're going to take a linear algebra class. And then let's get the algebraic rules out of the way. Whenever we do algebra, we should expect to have some rules and properties. Just shout out a few properties that you heard in high school or maybe college, things that we know about real numbers.
Whole number.
Whole number really isn't a property, it's kind of a definition, but think about the operations. What kind of things do we know about addition, for example? Does it commute? Does it associate?
Yeah.
Can we do distributive related stuff in the reals?
Yeah.
Okay, so we asked the same questions about vectors. These are new objects. Let's figure out what we're allowed to do. Algebraic properties of our n. So, what does that symbol mean?
For all.
I'm going to need more than 2 people to answer that question. What does this symbol mean?
For all.
Okay. For all vectors, we're calling those vectors u and v. And actually, we need a third one, so let's do w. What does that symbol mean? Everybody.
In.
Rn. So, by stating this, I'm claiming something about all 3 of these vectors. How many entries do all 3 of these have? There you go, that's how you read this. A semicolon is functioning as kind of like an and. C, D, in, R. In English, I could conceptualize this as, well, I have 2 scalar values, and I'm happening to call those scalar values C and D. Does that make sense? Okay. First property that we have, u plus v, is the same thing as v plus u. What do we call this typically in algebra?
Equals.
Addition.
Commutativity, they commute. U plus v plus w equals u plus v plus w. That's a very familiar property too. Which one do we call this? Yeah, associative. Now, some of you who haven't taken abstract algebra wouldn't know this one. But if I take 0 vector plus any vector, that's going to return to be the same vector. It's the same concept of if I took 0 plus 7, that's 7. No matter what I add to 0, it'll always return back to it. So the equivalent identity, that's what we call it, an identity for vectors is going to be the 0 vector. That will, if you add it, it will return the vector. 4 is that we have inverses. That's the math word we use. There exists for every vector u another vector minus u, such that this is going to return you to the identity of your group. Okay. So this, have any of you taken higher algebra yet? Oh, okay. Fun fact, if you do take higher algebra, these are an expression of the properties known as group properties, and more specifically, the abelian. Question? Abelian group properties. Abelian because of this. Okay. So if math seems to rhyme, the higher you go up in math classes, that is why. There are a few more properties that's going to distinguish this from just a plain old group. It's actually a vector field. So that means we have some additional properties here with our scalar multiplication. So 5 is going to be that we can distribute in this way. I can take 2 vectors that are added together and distribute through my scalar multiplication. So this is going to be Cu plus Cv. I can also distribute through scalars. So if I add 2 scalars like this, and then have a vector multiplied, then I can do the scalar multiplication like this as well. there is a type of associativity that happens. I could take a scalar and then have a scalar times a vector. And that's going to be exactly the same as if I just choose to simplify my scalars first and then have the vector. That actually proves to be really practically useful when you have an annoying scalar here that you can pull out and then simplify so that the vector you're handling is not as horrible. And then the last one is we do need an identity functioning for the multiplication. So 1 times any vector will return the vector. So this is the multiplicative identity, additive identity.
That's a scalar one, correct?
Correct, yes. The only reason I'm not putting a dot in there is because that could look like a dot product in linear algebra, and I don't want to do that. Yeah, math, the word product got commonized. I mean, there's dot products, cross products, Cartesian products. Yeah, this rag is amazing. Okay, so that was the warm-up. We have the language we need to actually talk about now, the fun stuff, okay? So if there's a time to lock in, it's going to be the rest of this lecture because you're going to use it for the entire rest of the class. Given a set of vectors, v1 to vp. So what does this notation communicate? This communicates I have a list, undetermined number of lists, but I know for sure that there are exactly p items in this list, okay? And these are going to be vectors in Rn. So how many entries do all of these vectors V have? Good. And then I have a list, the same number of the scalars. Then the vector y, the vector y defined by, so what we do is I'm going to pair the scalar with each vector. So C1 is going to go with V1. You can imagine that goes on so on and so forth. So C2 with V2, C3 with V3, until we end up with CP, the pth one, to VP. And we're going to call this is called a linear combination. Those two words are going to be some of the most important vocab for this entire unit, okay? Linear combination of the vectors v1 through vp with, and we actually do have a specific name for what these coefficients are. We call these the weights. Weights, c1 through cp. Does this make sense? Okay, let's see some examples of linear combinations. So if I took something like 10 times the vector v1 minus 7v2 plus v3, this is a linear combination of the vectors v1 through v3. How do I know? Well, it's because I took a weight, multiplied it by its corresponding vector, added another weight, which happens to be a negative weight, to another vector, and then added another weight, which is 1 in this case, to that. Don't freak out if the numbers start to look really goofy or even 0. So I could have maybe like the square root of 5 times a vector. Maybe plus 0 times a vector. That is totally allowed because is 0 a real number?
Yes.
So it's possible. Yeah. Minus like maybe a fraction. Don't get tripped out by different types of real numbers. It's all still just a linear combination. And then now that we know what a linear combination is, I can kind of give you a more formal idea of what the 0 vector really is. The 0 vector is going to be essentially the vector that has all weights that are 0, irrespective of how many components I have. So 0 v1 plus 0 v2 plus 0 v3 plus, doesn't matter how many components I could have, any number, arbitrary number of components, this is the definition of 0 vector. Is there a difference between 0 vector and the scalar 0? Yes, huge difference. The scalar 0, is the scalar 0 a vector? So does that make that definitionally not a 0 vector? Yes. So if you write 0 when the answer is 0 vector, do I reserve the right to count that as the scalar 0 points? Yes. Okay. All right. Let me grab my. What time is it?
41.
Oh, beautiful.
You still have 2 hours.
We just missed the experimental method.
Okay, so let's recall. So most of this class is recalling former concepts and then repurposing it in terms of different expression. So I'm going to make an augmented matrix here, just an arbitrary one to work with. So we got 1, 6, 0. This is a subtle detail. I'm going to point it out now because it's useful. The way I'm going to start writing these matrices is not in row by row. I'm going to start putting them column by column. And if you remember what the very first definition was, it was a column vector. In other words, if I start thinking, the way I handwrite my math changes the way I actually conceptualize the problems I'm solving. And the people in Calc 3 know that I am a huge stickler on doing good handwritten work because you will solve more problems more accurately if you do that, okay? So -1, 2, 2, 4, -8, -1, and then this is the arbitrary dotted line that doesn't really exist. And then 10, 10, 7. So, vocabulary time. Remember that we called this an augmented matrix. We call it augmented because we intend to signal that this final set apart thing is like the equals and then the constants. And so, really, like I already suggested, if I write these as columns, are these not just vectors themselves if I isolate every single one, right? So if I just isolated that, well, that's a column vector. That's a column vector. All of these are just column vectors. And so we can start giving these names. I'm going to define A1 to be the column vector of the first column, right? So A1 would be this first column, 1, 6, 0. Did what I just do make sense?
Yeah.
Okay. Ergo, what is the column vector A2?
-1, 2, 2.
Yeah, -1, 2, 2. And column vector A3, what is that?
4, -8, and -1.
Yeah, 4 minus 8 minus 1. Now, for an augmented matrix specifically, since I know that if I wrote this as a system of equations, this is like the equals and then the constant on the other side, we're going to call this a different type of thing. We're going to break away from the columns, call this B. We'll get way more into why we do this in the next following sections, but for now, just trust me. And this would be 10, 10, 7. Okay, so if we do this, we open up a whole new perspective to represent these kinds of systems through vector equations. And again, if we can visualize this, if we wrote it out as a system of equations, I would have x1 minus x2 plus 4x3 equals 10. Yes? So that's the first equation. So then what would the second equation be under it?
6x1
And then,
0.
right, 0x1.
Plus 2x.
x2 minus 1x3.
Okay. So what I'm going to try to train your brain to do is when you write your system of equations like this, the reason why we want to write it in this very specific form, all nice and organized, this isn't just to make OCD people happy, okay? Just to make your life happy, because really think about separating out these columns now. By inspection, given any linear system like this, you can already identify a 1, 6, 0, a -1, 2, 2, a 4, -8, -1, a 10, 10, 7, translate between those two. Get used to translating between those two. I know that it's not in itself a remarkably complex or profound mathematical concept, but you would be shocked how stunningly easy it is to go between these, and how many problems that look hard can be made super easy by being able to go between these two things, okay? It's about perspective, not necessarily about computation at this point. So I could represent this as a linear combination. I could say my x1 component, whatever that variable is multiplied really by the column vector 1, 6, 0. And then the next one, what's the next one?
Negative 1, 2, 2.
What's the next one?
1, negative 8.
And then equals the b vector, right? So suddenly we can translate a system of equations problem. We could think about it as an augmented matrix. In addition to thinking about it as an augmented matrix, we could also think about it as a linear combination of just some vectors. And in that perspective, what that's really saying is imagine the x1, x2, and x3 are like your tuning dials on a radio, and you're trying to achieve this signal. And you're adjusting these weights. And if you're able to find and scroll through and get a combination of twisting and turning and adjusting the values of x1, x2, and x3 so that these can spit out this, you've got yourself a solution. So it reframes the concept of solving an equation. We could think about it as solving a system. Further, we could think about it as reducing an augmented matrix. And now we've given ourselves a third window to look at. Finding the right weights to adjust some vectors to tune to the right signal, to the right vector. All three of those statements will produce precisely the same exact thing logically. And that's pretty cool. And that's where a lot of these different STEM fields are going to intersect, is through these three perspectives. Okay? Does that make sense?
Yes.
Let's keep moving. And I'm going to show you some notation. But I wanted to really write all of this out because if you see it with an example, then the more general kind of definition notation will make more sense. Okay. So here's an important note. A vector equation x1, a1, et cetera, like we had up until, we'll make this general to n pieces. And then we have our b vector over here. This has the same solution set. This is really just reiterating what we just talked about as the linear system. Linear system whose augmented matrix is, and then here's the notation, okay? So instead of like writing out the whole thing, I know that A1 represents like the whole column. So that vector is itself the column that is the first column of that matrix. And then there would be the second column, the third column. How many columns we have? In this case, we have n columns. And then after we finish the column vectors, for the augmented matrix, we separate out the coefficients, which would be in this case like our coefficients over here in the B. Does this notation make sense in light of what we've been doing over here? So if you saw in the textbook and it's trying to give you something that looks kind of funny like this, and they're telling you that this is an augmented matrix, you're trying to draw the dots of how on earth that is an augmented matrix. Think about the weights and think about these column vectors actually coming from a system. Okay? Let's see. I'm going to write it on this side because I'm wearing out of space. You know, there's a very, very particular type of just know that the Lord is with us. He is with us. I know He's in this room. I can feel it. I think we forget he likes math. He kind of thought about it and made it. Takes delight in people who take the time to study it. And that happens to be you guys. So, relish in the opportunity. B can be generated by a linear combination of some column vectors. Again, so by convention, you've probably noticed I use A's when I'm talking about columns. This is true if and only if. So these are going to be logically equivalent statements. There exists some sort of solution. Have I written this on the board yet in this class?
No.
Okay. This funny looking backwards capital E, this is the there exists. It's a statement of existence. If I were to put a slash through it, that means I'm saying it doesn't exist. And if I put an exclamation mark next to it, like, it exists, it's unique, okay? So there's a solution, and I can describe that solution by a vector x, like we were talking about. Like, remember the system where it had x1 through 2, and then those were the weights themselves? In a similar sense, these weights in that linear combination then form what we mean by the solution to the linear system. To the linear system corresponding to the augmented matrix. Okay, so there's a lot of terminology floating around. There's a lot of different representations, a lot of different perspectives. Are we feeling good about this?
Yes.
So if I want to find a vector B as some kind of, think of this, we're trying to tune a radio signal into this by adjusting our weights on these inputs. Yes, question?
Just double checking the notation. So it's x sub 1 to x sub n? Or is it a
Yes, my bad, that looks terrible.
Okay.
This is an N. Thank you.
Perfect, thank you.
Anything else? Because I'm very excited. I made a cute little graph here for you guys, so we'll cover this now. So if you really needed to summarize the entire section, you can do so if you handwrite this graphic that I'm gonna make, okay? This is bugging me just a little bit, so I'm going to figure out how I'm going to do this. I think I'll fit it all over here. Okay.
Maybe we should pass more towards the wall and just use the entirety of the white.
The white wall, yeah. So if I have a system of equations, so there's alpha x1 plus blah, 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 right? This is just a linear equation. And then we have a certain amount of equations. I can already kind of hear the questions. Alpha, beta, these don't mean anything. I just needed a placeholder like variable or symbol to indicate that there's going to be some constants. So this could be like 1, a 7, a 3, a 5, a 10, negative 8, whatever, right? X1. So this, if I could start with a system of linear equations, then I could think about this in terms of an augmented matrix, right? So I could think about this in terms of, I'll move it over here, an augmented matrix, which the rows then become, I would just strip out all the things, so it would be alpha 1, blah, 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 up to alpha n, and then all of the coefficients down. And then I separate out, obviously, the B1 through Bn on the other side of the equal sign. And so this is an augmented matrix. Okay. I could also think about this in terms of a vector equation. where I take the columns out. So I have x1 times my alpha 1 through beta 1 plus, and then however many columns that we have. So we have n columns in this case, so up through xn, alpha n through beta n. And then this is equal to a b1 through bn. So this is a vector equation. This is the title of today's section, vector equation. We could also more simply think about each of these columns as just, this is column A1, this is column A2, 3, 4, 5, up through column AN. So if I wanted to, I could say, that's just the same thing if I was able to write them as x1 column vector A1 through, etc., to the nth column equals the b vector. So these are both vector equations. And actually, you could go from that system, if you look back in your notes and I kind of dotted it out, you can go directly to this perspective from the system of equations if you wanted to, and go back and forth between those. And then if we wanted to think of our augmented matrix in terms of column vectors, I could just put the first column as A1, and then continue marching across until I get to my nth column, and then designate off my b vector as the last column vector. So that you can achieve by going through this perspective. In a similar way, you can get that perspective from here, which, from this vector equation, you could also think of these as being equivalent. And then lastly, the system here itself, you can represent immediately as that. All of these perspectives are exactly the same thing. All the same solution set. So, here's my guess, is that this is a little bit abstract and not very tangible anymore. So I'm going to go through an actual, with a system with numbers in it, and then walk through all of these perspectives and what all of them look like, okay? So give me a thumbs up when you've got everything kind of how you want in your notes. And then worst case scenario, this is going to be on the internet, so you know, you can always go back. Okay. What time is it?
Basically, honest.
Did you get a picture of it?
Okay.
Put it in the Discord.
So suppose we have an actual system of equations with numbers in them, okay? 4x1 minus 3x2 equals 6. 7x2 plus 8x3 is equal to minus 1. 5x1 minus 10x3 is equal to minus 8. So what do we call this? If it's presented to you like this, what do we say? System of equations, yes, okay. So this is our system of equations. Let's explore all of the perspectives we can take on this. We could, the first one was just make it an augmented matrix, right? So let's name these out by the column vectors. What would the first column be?
4, 0, 5,
Second column?
-3, 7,
Third column?
0, 8, -10,
And then we separate out the b constants to what column?
6, -1, -8.
Okay, so what do we call this representation?
Augmented matrix.
Augmented matrix. Beautiful. Okay. And then we've discovered today we could do vector equations. So then the perspective would be, I start with my x1 weight. What vector is being scaled by that one?
4, 0, 5,
And then let's continue.
-3, and then x2, -3, 7, 0.
-3.
x3,
Plus x3.
0, 8, -10.
0, 8, -10. Equals
6, -1, -8.
And we call this a what?
Vector equation.
Now, if I want to think about this as A1, this as A2, this as A3, and this as B, as the conventional naming system, then I could say this is x1, A1, plus x2, A2. What would the next one be?
X3, A3.
Further, what if I wanted to rewrite this augmented matrix in light of the columns A and B? So this would become just A1,
A1, A2, A3.
A2,
And then B.
A3, and B. Okay, so this is all the perspectives we have unlocked so far. There's a reason why we're calling these A1, A2 column vectors, because when we get to the matrix equation, we'll actually start defining a capital A matrix being composed of columns A1, A2, etc., etc. Let's see here.
I got a question.
Yes.
So in the test, can you put the A1, A2, A3, B?
Well, it depends, right? Context is huge. If you're only given the columns without any explicit numbers, then sure, that'd be the only way you could do it. But if you're actually asked to compute something and you're provided with numbers, you need to be using this perspective. Yeah? Anything else? Okay. So it's what, like 8 minutes left? Okay, that's enough time. I'll at least introduce this topic. It's actually really important, so I might still upload a little bit more. But let's
We're back.
okay. Definition. Given V1 through Vp, so we have P vectors, and we're going to give them all n entries, so they're all in Rn. A set of all linear combinations, of these vectors, so of V1 through Vp, is denoted by, we have this thing called span, and then it'll be the span of V1 through Vp, and is called the subset of Rn spanned, or we can think of this as generated, they're equivalent, by the vectors that are listed in that set, so V1 through Vp. That is, span of a set of vectors V1 through Vp is the collection of all vectors that can be written in the form C1 V1 plus C2 V2, so on and so forth, until we get to CP VP, where we know that those are scalar weights. C1 through CP are scalars. Okay, there's a math notation thing. This is the first definition that, in my opinion, makes less sense in English than it does with just math notation. So the mathematician would simply say, okay, the span of some vectors V1 through Vp is a set. What kind of set, do you say? Well, let's see what's in here. I want a linear combination, and by definition of a linear combination, I have some sort of scalar weight multiplied by each one of these vectors, and I add all of those up. So I go all the way through with how many different weights? Well, C1 through CP, depending on how many. And all of these are scalars. So how do I read this? Everyone say it with me. Span of the set of vectors
The set of vectors
V1 through VP
V1 through VP
is equal to
is equal to
the set
the set
of linear combinations
of combinations
C1 V1
C1 V1
through CP VP
CP
such that
such that
C1 through CP
C1 through CP
are real numbers
are known
or scalars. Okay? So this is more than just notation. I'm teaching you how to read math, because if you know how to read math, most of the stuff in this textbook really isn't actually that difficult. Okay? It looks difficult because they don't assume you know how to read this. So they have to do all of this English when, if you know what this math says, you can just write it in a single line. So study hack, just know how to read this, because then you don't need to memorize these chunks and paragraphs of explanations. Okay? Let's see. So what I'm going to do is I'm not going to rush through this, because if I rush through this, I'll create more confusion than help. And I'm going to record this separately and then add it to like a little span section in the YouTube playlist. Before we finish up, just a few housekeeping notes that I included in a D2L news item. I am assuming you're all grown adults. Check the D2L regularly for news updates. If I post something to the news feed, as soon as I hit submit, I'm assuming within about 24 to 48 hours, all of you have not only read the information in there, but are aware of what's going on in the class, okay? If you are unaware because you didn't check, that is not my responsibility. So that includes anything with exam reviews, grading stuff, office hours, etc. On my way out of this classroom, I'm going to remember what my office number is. And I'm going to add that to the D2L shell. I just sorted out my schedule, and I have a Saturday office hours again, so I'll put that on the D2L shell as well. If you need help, ask for it, please. I have my email, my number, everything on there. Does that make sense?
Yes.
Okay, thank you.